Space is not empty. The sun does not sit still while everything else moves around it. And gravity has never actually been a pull, despite what nearly every description of it still assumes. Physicists have carried the corrected version since Einstein published it in 1915. Most classrooms still teach the older one, from Newton, instead. Replace the sun with a black hole of the exact same mass, and Earth's orbit does not shift by one measurable second. 95% of everything astronomers can detect in this universe is neither a star, a planet, nor a black hole. Tonight, we take apart 12 things you believe about this universe, including why a comet named Halley never drags its tail behind it, why a satellite called the International Space Station has been quietly falling toward Earth for 25 years, and why the number scientists call dark energy might be the largest admission of ignorance in the history of science. Gravity was never a force reaching out to grab you. It is the shape of space itself, bending around anything that has mass. Right now, at this exact second, you are being bent. Let's begin. Right now, your body is pressing down into whatever is holding it up. A mattress, a couch, the seat of a chair. With a force you can actually feel against your skin. Every physics class you ever sat through explained that pressure the same way. The Earth is pulling you toward its center. That explanation was formally replaced in 1915, and the replacement never made it into most classrooms. Here's what actually happens. Mass does not reach out and grab anything. Mass bends the space around itself, the way a heavy object settles into a stretched sheet and warps the surface near it. You are not being pulled down. You are following the straightest possible path through space that has been warped by the planet underneath you. And the floor is the only thing stopping you from continuing along that path. Drop a phone from shoulder height. Nothing reaches out to seize it, and nothing needs to. The phone was already moving in a straight line through curved space the instant it left your hand. The floor is the interruption, not gravity. That correction breaks an assumption you've carried since childhood. That falling and floating are opposites. They're not. An astronaut orbiting 250 miles above Earth right now is not weightless because gravity stopped reaching that high. At that altitude, gravity is still about 90% as strong as it is on the ground. The astronaut is weightless because they're in free fall, following the same curved path a dropped phone follows, except moving sideways fast enough that the curve of the fall matches the curve of the planet underneath it. They fall forever. They never land. An astronaut on the International Space Station is falling, constantly. The station is falling too, at the same rate, which is the only reason anything inside it appears to float. None of this makes Isaac Newton's original description wrong to have used, or foolish to have taught for over 2 centuries before anyone corrected it. Isaac Newton's version of gravity still works for almost every calculation an engineer will ever need. It gets a rocket to the moon using nothing but force, mass, and distance. What it cannot explain is why a beam of light bends when it passes close to the sun, because light has no mass for a force to grab onto. Nothing to pull. And yet, in 1919, astronomers photographed starlight doing exactly that during a solar eclipse, bending around the sun's edge by close to the precise angle Einstein's curved space model predicted, and by roughly double the angle Newton's force model predicted. Newton's gravity failed a real measurement that year. Einstein's geometry passed it. Not by a small margin, not by a rounding error. Newton's number and Einstein's number sat on opposite sides of the same photograph, and only one of them matched the plate. What you were taught wasn't a lie, it was a simplification small enough to fit in a classroom and comfortable enough that nobody thought to ask what it left out. So the pressure holding you into the mattress right now was never a hand reaching up from the center of the planet. It's the shape of the room you're lying in, curved by a mass more than 100,000 times heavier than every human being on Earth combined, and you are simply unable to fall through the floor along the straight path that shape demands. But if gravity is geometry and not force, something about the moon stops making sense. A force can be blocked, deflected, cancelled by an equal and opposite one. Geometry can't be argued with that way, and the moon has been falling toward Earth for 4.5 billion years, never once landing. Tonight will not resolve why finding out you were wrong about your own universe feels less like losing something and more like being let into a bigger room. We're going to sit inside that question instead of answering it. Isaac Newton pictured it first, in a thought experiment that still holds up better than most modern explanations of it. Imagine a cannon on a mountaintop, firing horizontally. A weak shot arcs downward and lands close by. A stronger shot lands farther away, but it's still falling, pulled toward the ground along a curve. No exceptions. Newton asked what happens if the shot leaves the cannon fast enough that the ground curves away underneath the ball at the same rate the ball is falling toward it. The answer is that the ball never lands. It falls past the horizon and past the next one, endlessly, tracing a full circle around the planet. That's not a metaphor for an orbit. That is the literal mechanics of one. The moon is doing exactly what Newton's cannonball does. At a distance of roughly 238,000 miles, moving sideways at something like 2,300 miles an hour, it is falling toward Earth constantly and missing constantly, because the curve of its fall matches the curve of an orbit wide enough to clear the planet entirely. Cut that sideways speed to zero, even for a moment, and the falling stops being an orbit. It just becomes falling, straight down, arriving in about 5 days. Nothing is holding the moon up. Nothing needs to. It's being bent by the same curved space bending you into your mattress right now, at a scale large enough that the bending closes into a loop instead of a stop. Here's the part almost nobody is told. This bending isn't just a chalkboard equation. It's been measured. In 1976, a spacecraft called Gravity Probe A carried an atomic clock to an altitude of about 6,000 miles and beamed its ticking rate back down to an identical clock on the ground. The clock, in weaker gravity, farther from Earth's mass, sitting in less curved space, ran faster than the one on the ground, matching Einstein's prediction closely enough to end the argument. Gravity doesn't just bend the paths objects take through space. It bends time itself. And by 1976, clocks had finally gotten precise enough to catch it happening. You have never once felt the moon actually fall, and you never truly will. It's too far, too slow, too patient for a body built to notice danger, not geometry. But you can watch the evidence of it happening anyway. The moon isn't just falling around Earth in a stable loop forever. Tidal forces between the two bodies are stretching that loop wider, year after year, by about 1.5 inches. Roughly the rate a fingernail grows. It has been doing this since long before anything alive was around to measure it. And someday, billions of years from now, the fall will have stretched wide enough that a total solar eclipse won't be possible anymore. The moon will still be falling. It will just be too far away to ever quite cover the sun again. That's not a small correction to a minor detail. That's a deadline, quietly running on an event most people assume is permanent. But bent space explains orbits. It does not explain the strangest object in tonight's sky. One that only swings past every 76 years, trailing a tail that, it turns out, almost never points where you'd assume it does. The 1919 eclipse wasn't actually the first time Einstein's version of gravity beat Newton's in a real measurement. It was only the most photogenic one. 4 years earlier, sitting at a desk with no telescope involved at all, Einstein had already solved a problem that had embarrassed astronomers for over half a century. The orbit of Mercury refused to close. Every planet's orbit is technically an ellipse that slowly rotates over time, its closest point to the Sun drifting to a new position with each pass. A wobble astronomers call precession. Mercury's ellipse rotates faster than Newtonian gravity, accounting for every tug from every other planet in the solar system, said it possibly could. By a small but stubbornly persistent margin of about 43 arcseconds per century, roughly the width of a coin viewed from 2.5 miles away, repeated every 100 years without fail, the French astronomer Urbain Le Verrier flagged the discrepancy in 1859, and for the next 56 years, the leading explanation was that an undiscovered planet, nicknamed Vulcan, had to be orbiting even closer to the Sun than Mercury. Its extra gravity accounting for the missing wobble. Astronomers searched for Vulcan for decades. Vulcan was never found, because Vulcan never existed. In 1915, Einstein ran Mercury's orbit through his new equations for curved space-time. With no invented planet added anywhere in the calculation, the answer came out to almost exactly 43 arcseconds per century. The missing wobble, explained in full, using nothing but the curvature of space around the Sun itself. No new planet, no new force. Just the correction this entire episode keeps circling back to: solving a 56-year-old mystery on paper, 4 years before a single photograph confirmed it during an eclipse. By his own later account, Einstein was so certain the number would match that he described feeling something close to physical illness in the minutes before finishing the calculation. Heart palpitations, he called it. From a man not usually given to that kind of language about his own work, Mercury sits close enough to the Sun that the curvature of space around that much mass is unusually steep for a planet, steep enough that its orbit is the one place in the entire solar system where Newton's approximation frays first, long before any other planet shows the strain. Every other planet's orbit obeys Newton's version closely enough that the difference never mattered to anyone building a bridge, launching a rocket, or plotting a course to the moon. Mercury was always going to be the planet that gave the old model away first, simply for sitting closest to the one object, massive enough to bend the rules loudly enough to notice. The lesson tucked inside that detail is worth carrying forward. For a century, the correction wasn't hiding in some far corner of the universe. It was sitting in the innermost orbit of your own solar system the entire time, one planet away, waiting for someone to do the arithmetic honestly, instead of inventing a planet to make the old answer keep working. A comet's tail looks exactly like a trail. The streak a car leaves in dust, or a scarf trailing backward from whoever's wearing it, pointing behind the object as it moves. That image is completely wrong, and Halley's comet proves it in a way that would look like a mistake in a movie. For roughly half of Halley's 76-year orbit, the comet is moving away from the Sun, retreating back out toward the edge of the solar system. And for that entire outbound half of the journey, the tail still points away from the Sunday. It's pointing ahead of the comet, leading the way, not trailing behind it. A scarf flying in front of the person wearing it. If you'd stood on Earth in March of 1986 and watched Halley through a telescope, you'd have seen exactly this happening. Though almost nobody explained it that way at the time. That same month, a European spacecraft called Giotto flew within 400 miles of the comet's nucleus. The first time any instrument had photographed the solid core of a comet up close, and confirmed that the tail wasn't coming from the nucleus streaming backward at all. It was gas and dust being torn loose from the surface and shoved away by the Sun, regardless of which direction the nucleus itself happened to be moving. Here's the mechanism nobody puts in the popular version. A comet's tail isn't exhaust, and it isn't motion blur. It's gas and dust boiled directly off the comet's surface by sunlight, and once that material breaks free, it stops caring about the comet's velocity entirely. The solar wind, a constant stream of charged particles racing outward from the Sun at over 1 million miles an hour, physically shoves the loose gas away from the Sun in a straight line. Radiation pressure, sunlight itself acting as a physical force, pushes the heavier dust away on a slightly curved path. Neither force has any idea which direction the comet is actually traveling. So Halley doesn't grow one tail, it grows two, and they visibly split apart from each other in photographs. The ion tail is thin, blue-tinted, made of charged gas, and points dead straight away from the sun, rigid as a compass needle, capable of changing direction within minutes if the solar wind shifts. The dust tail curves, sagging along the comet's orbital path the way sand thrown from a moving car settles into a soft arc behind it, because dust is heavy enough to still remember a little of the comet's own motion. Photograph Halley near the sun, and the two tails visibly fork, one rigid, one curved, aimed in almost, but not quite, the same direction. Pause on that. Every comet in the solar system is being pushed by the same invisible wind all the time. Whether it grows a tail bright enough for you to see or not, the wind doesn't care where the comet came from, or where it's headed. It only cares where the sun is. Gravity just bent your understanding of what holds the moon up. The solar wind bent your understanding of the one object in the night sky that looks the most like it's simply moving forward. Neither correction has touched the biggest one yet, and it would turn out to be the one that made the entire solar system look less like a solar system and more like something spiraling. Here's the part almost never mentioned alongside the two tails correction. The solar wind itself, the invisible stream of particles doing all that pushing, was first seriously proposed because of exactly this comet behavior, decades before any spacecraft could fly out and confirm it directly. In the early 1950s, the German astronomer Ludwig Biermann was studying photographs of comet ion tails and noticed something that radiation pressure from sunlight alone couldn't account for. The tails weren't just pointing away from the sunday, they were accelerating away from it, snapping into new alignments within hours whenever the sun's activity shifted. Far too fast and far too strong a push for light pressure by itself to be the whole explanation. In 1951, Biermann proposed that the sun had to be emitting something else entirely, a continuous, outward stream of charged particles, invisible, constant, blowing through the entire solar system, whether any comet was there to reveal it or not. The American physicist Eugene Parker picked up the idea in 1958 and worked out the physics in full, coining the term solar wind in the paper that first predicted it mathematically. The paper was initially rejected by reviewers who considered the idea implausible. Parker's editor overruled them and published it anyway. Direct proof arrived in 1962, when the Mariner 2 spacecraft flew through interplanetary space carrying instruments built specifically to detect charged particles and measured the wind exactly where Parker's equations said it would be, moving at the speed his math had predicted years earlier from nothing but a comet's misbehaving tail. That wind is still blowing past you right now, and has been for your entire life, even though nothing about sitting on the surface of Earth ever makes it feel that way. Earth's magnetic field deflects almost all of it before it reaches the ground, the same shielding that turns a portion of the wind into the aurora when it does slip through near the poles. Astronauts on the space station, and every instrument riding along with them, sit close enough to the edge of that shield to measure the wind directly, hundreds of miles above your head, at speeds that can exceed 1,000,000 miles an hour during an active solar storm. Biermann never lived to see dark matter's rotation curves, or a black hole photographed. He died in 1986, having spent the tail end of his career watching Parker's once-rejected prediction become one of the most measured, most mapped features of the entire solar system. Confirmed, ultimately, by hundreds of spacecraft that have since flown straight through the same wind, a comet's crooked tail first gave away. Parker himself lived to see it too, and then some. He was still alive in 2018 when NASA launched a spacecraft built specifically to fly closer to the sun than anything ever had, into the wind he'd first described on paper 60 years earlier and named it after him while he was still around to watch the launch. The Parker Solar Probe, the first NASA mission ever named for a living scientist. He passed away in 2022, having spent 6 decades watching an idea rejected by his own reviewers become sturdy enough to put a spacecraft's name on. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. Every diagram of the solar system you've ever seen shows the same thing. The sun sitting still in the middle, planets tracing flat circles around it, like grooves cut into a record. That picture is only true if you freeze the sun in place. The sun has never once been still. The sun is moving through the Milky Way at roughly 200 kilometers every second, dragging the entire solar system along with it. Every planet, every moon, every comet still finishing its slow lap around a star that refuses to sit down. That sideways speed is close to 7 times faster than Earth moves around the Sunday. The circle Earth traces every year isn't a circle at all, the moment you stop pretending the sun holds still at the center of it. Now add Earth's own orbital motion on top of that. Watched from outside the solar system, Earth's yearly loop barely has time to curve back on itself before the entire system has already moved hundreds of millions of miles further along. The result isn't a flat ring of overlapping circles. It's a long, gently drawn-out spiral, stretched almost straight by how much faster the system moves forward than any planet moves around it. Here's the part that got exaggerated the last time this idea went viral. Some animations drew that spiral as a tight corkscrew, coiled like a spring, planets whipping in fast little loops behind a racing Sunday. That version overcorrected. The real pitch of the spiral is shallow, so shallow that, drawn to scale on a page wide enough to show the whole thing, Earth's path would look almost like a straight line, with the faintest wobble folded into it, not a spring. Closer to the wake, a boat leaves on still water, drifting almost imperceptibly side to side as it crosses the lake. You have never once retraced your own position from a year ago, not on the calendar and not in space. Earth doesn't return to the same point in the universe every January. It returns to the same relationship with a sun that has already carried it somewhere else entirely. Here's a number that makes the drift concrete. Over the course of one ordinary human lifetime, roughly 80 years, the sun's motion through the galaxy carries this entire solar system a distance equal to more than 3,000 times the gap between Earth and the sun itself. Every planet, every moon, every spacecraft ever launched has been dragged along for that ride without a single one of them completing so much as one lap of the galaxy's actual center. A full galactic year. One true orbit of the sun around the Milky Way takes something close to 230 million years. Every human being who has ever lived did so during roughly the same 1,000th of a single galactic year. That correction sounds abstract right up until you ask what it does to time itself. Because 1 year only means something if you're standing still enough for a clock to agree with you. And nothing in this solar system is standing still. Put 2 identical, perfectly synchronized clocks in the same room. One on the floor, one on a shelf a few feet higher. And wait, they will not agree. The one on the shelf, sitting in very slightly weaker gravity, runs very slightly faster, and the gap is not a rounding error in a bad instrument. It's real time, passing at a different rate, over a height difference you could clear with one stare. This isn't a rare effect that only shows up near black holes or inside physics labs built for the purpose. It's constant, everywhere, at every altitude. And in 2010, physicists at the National Institute of Standards and Technology measured it directly using optical clocks precise enough to catch the difference in time's passage across a shelf barely a foot higher than the one beneath it. Higher clock, weaker gravity, faster time. Every single time. So the now you're experiencing right now is not technically the same now. Your own feet are experiencing compared to the top of your head. The difference is far too small for a human nervous system to notice. It is not too small to matter to a satellite. Global positioning satellites orbit roughly 12,000 miles up, sitting in gravity meaningfully weaker than the gravity at your address, and moving fast enough to add a second effect on top of the first, because speed also slows a clock down, the same mechanism that would let a fast enough spacecraft's crew age slower than everyone they left behind. Weaker gravity speeds a GPS clock up. Orbital speed slows it back down. The two effects don't cancel each other out. They combine into a net drift of roughly 38 microseconds every day. Hold that number. 38 microseconds sounds far too small to matter to anyone standing on the ground, holding a phone, waiting for directions. But GPS timing works by multiplying tiny time differences by the speed of light to calculate distance, and left uncorrected, that daily drift compounds into a positioning error that grows by roughly 6 miles every single day. Not 6 miles total. 6 more, every day, stacking on top of yesterday's 6, and the day before that. Within a single week of no correction, a GPS receiver would be confidently placing you in the wrong town. Within a month, the wrong state. Every GPS satellite in orbit carries a chip program to subtract that exact drift before your phone ever sees the signal. You have almost certainly never thought about it. But the device in your pocket is running a live correction for general relativity every time you ask it for directions to a restaurant, checked against a theory most of the people relying on it have never read a page of. Working correctly enough that you've never once had a reason to doubt it. 38 microseconds is the smallest version of this disagreement you'll hear about tonight. It will not stay the smallest. Before this episode is over, the gap between two clocks stops being measured in millionths of a second and starts being measured in years. When engineers built the first GPS satellites in the 1970s, not everyone on the project agreed that Einstein's correction was actually necessary. The effect seemed too small, too theoretical, and a few of the physicists involved were confident enough in that doubt that the very first satellite's clock was built with a switch, a way to turn the relativistic correction off entirely, in case it turned out to be an unneeded complication running on expensive hardware in orbit. They tested their own doubt honestly, the way you'd expect an engineer to, rather than a believer on either side of the argument. The switch went off first, deliberately, so the drift could be measured against a theory instead of just assumed away in either direction. Within hours, the satellite's onboard clock had drifted out of agreement with clocks on the ground by an amount that matched Einstein's prediction almost exactly. Almost exact down to a level of precision that left the skeptics on the project with nothing left to argue and no honest way to keep the switch flipped off out of professional pride. Einstein won the argument in hours, against engineers who had every incentive to be right instead of correct. The switch was turned back on, and it has stayed on in every GPS satellite launched since. Nobody proposed testing it again. You are, at this moment, likely carrying a small object in your pocket that quietly settled a real scientific argument decades before you were born and never once mentioned it to you. It's worth sitting with how unusual that is. Most scientific disputes take decades to close. Competing papers, competing labs, careers spent defending one side or the other, sometimes outliving the scientists who started the argument. This one closed in an afternoon because the two clocks either agreed or they didn't, and there was nowhere for a skeptic to hide once the numbers came back. Not every argument in physics gets to end that cleanly. This one did, and almost nobody old enough to use a smartphone today was alive to see it happen. 4 corrections in, and none of them were really about space, out there. Gravity, a comet's tail, the shape of your own yearly orbit, the clock in your pocket. Every mistake corrected so far has been about something close enough to touch, watch, or carry in a coat pocket. Ordinary objects, ordinary distances, and still, every single one of them turned out to be misremembered. That was the easy half of tonight. Here's the harder question hiding underneath it. If ordinary physics gets misremembered this badly for objects sitting a few feet away or a few thousand miles up, what's actually happened to the version of the universe most people carry around for the things nobody can stand next to at all? The inside of empty space itself, a black hole, or the edge of everything that exists? Nobody carries a phone that quietly corrects for any of those. Not yet. 250 miles up, where the International Space Station orbits, most descriptions of space stop using the word atmosphere and start using the word vacuum instead. Neither word is quite right. At that altitude, Earth's atmosphere hasn't ended. It has only thinned down to somewhere between 1 trillion and 1 quadrillion times less dense than the air filling the room around you right now. Thin enough to walk through without ever feeling it, and still thick enough to matter to something moving as fast as a space station. The ISS travels at roughly 17,000 miles an hour to stay in orbit at all, and at that speed, even a nearly vacuum atmosphere stops behaving like nothing and starts behaving like a very persistent headwind. Every second, the station collides with stray molecules of oxygen and nitrogen that never quite thinned out to zero, and every collision bleeds away a sliver of its forward speed. Lose enough speed, and an orbit stops being an orbit. It becomes a very slow, very expensive way to fall, one collision at a time, for years, without ever once feeling like falling to the people living inside it. Left alone, with no engine ever firing again, the ISS would lose something like 1 mile or 2 of altitude every month, on average. More during the years when the sun is especially active, because a more energetic sun heats the upper atmosphere and puffs it outward, thickening that faint headwind well above where it normally sits. The vacuum of space, it turns out, has weather, with good months and bad ones, the same way a coastline has calm days and storm days. You've probably pictured an orbiting object the way a coin sits on a table. Placed, settled, staying put until something moves it. Nothing in orbit is settled. Every satellite you have ever seen photographed against the black is losing a fight against friction so faint it would never register on any instrument built for use on the ground. And every one of them is on a clock, whether its engineers advertise that fact or not. Satellite operators built an entire discipline of mathematics around exactly this problem, called orbital decay modeling. And it matters more today than it ever has before. Tens of thousands of satellites share Earth's orbit right now, and a growing share of them, including most of the thousands making up newer low-orbit networks, are deliberately placed low enough that this same faint atmospheric drag will pull them back down and burn them up within a few years of the day they stop working, without a single ground command ever being sent. The same force threatening a £250,000 space station is, for a newer generation of far smaller satellites, treated as a built-in trash collector. You will almost certainly never see any of it happen. It happens anyway. On a schedule nobody advertises, above your head, most nights, in the same sky you were taught to think of as an unmoving, frictionless void, which is why the International Space Station carries something almost nobody associates with a laboratory: a fuel budget, spent entirely on standing still. Roughly once every month or two, a docked spacecraft fires its engines for several minutes, nudging the entire £250,000 structure back up to a higher, safer altitude. A maneuver so routine that most of the astronauts living aboard barely mention it, and so essential that skipping it for long enough would eventually end the station's 25-year run in the sky, one quiet mile at a time, with no dramatic moment marking the point of no return. Not gradually, not gently. In July of 1979, a different space station found out what happens without that budget. Skylab, America's first, had been left in orbit without a way to reboost itself, on the assumption that its altitude would decay slowly enough to allow years of advance warning before re-entry. Then the sun entered an unusually active stretch, well outside anyone's forecast. The upper atmosphere swelled further than anyone had modelled, and the drag Skylab was fighting increased faster than engineers on the ground could compensate for. The station's orbit collapsed years ahead of every prediction. NASA lost the ability to choose exactly where the 77-ton station would come down, and on July 11th, it broke apart over the Indian Ocean and Western Australia, scattering debris across a stretch of land near a small town called Esperance, whose local government, only half joking, mailed the United States a littering fine that went unpaid for 30 years, until a radio host finally covered it in 2009. That's what empty orbit does to a structure nobody keeps paying close enough attention to. It doesn't stay empty. It doesn't stay patient. And it never once sends a warning that arrives on a schedule anyone finds convenient. Picture the schedule NASA had been counting on before that summer. Years of advance notice. A controlled re-entry planned carefully over open ocean. No surprises for anyone standing underneath the sky. None of that survived contact with a sun more active than any forecast had assumed. Engineers spent the station's final months recalculating its remaining lifetime almost weekly, watching a deadline that kept arriving sooner, no matter how carefully they revised the model, until the choice of where it landed was no longer really a choice at all. You've probably never once looked up and wondered whether anything currently in orbit above you is already living on borrowed time. Most of it is, in one form or another, quietly spending a fuel budget or quietly running out of one. What you were taught wasn't a lie. It was a simplification too small to hold what's actually out there. Too small for the drag in an orbit called empty. Too small for a station that has to keep spending fuel just to remain exactly where it already was. Here's an idea that feels so obviously true it rarely gets questioned. Somewhere between Mars and Jupiter, a planet used to exist, and something. A collision, an explosion, a catastrophe, tore it apart, scattering the wreckage into the asteroid belt that orbits there today. Every single rock in that belt, once properly counted and weighed, argues directly against it. Add up the asteroid belt's entire mass. Every asteroid, every fragment, the dwarf planet Ceres included, which alone accounts for roughly a third of the total. And the sum comes to less than 4% of the mass of Earth's moon. Itself already the smallest thing in the neighborhood, most people are used to thinking of as small. Spread that thin across a ring of space wide enough to fit hundreds of Earths side by side. And there simply isn't enough material out there to have ever been a planet in the first place, let alone one large enough to shatter dramatically. The real explanation is quieter, and, in its own way, sadder. Nothing out there ever finished forming. In the solar system's first few million years, dust and rock in that region were colliding and merging the same way material was clumping together everywhere else, slowly building toward a planet the way every other planet built itself. But Jupiter, the solar system's largest body by an enormous margin, sits close enough to that belt that its gravity kept interrupting the process, stirring the rubble into faster, more violent collisions before it could settle into a single peaceful body. Every time the material there got close to becoming something, Jupiter shook the table. Now add the second piece to that picture. Jupiter isn't just the reason the belt failed to become a planet 4.5 billion years ago. It's still doing the same job tonight, nudging asteroids out of stable orbits often enough that a small number of them, on any given year, get redirected toward the inner solar system instead. Picture the belt the way most movies show it, a dense, chaotic field of tumbling boulders. Spacecraft weaving between near misses just to get through. Real spacecraft have crossed it more than a dozen times since the 1970s, and every one of them passed straight through without adjusting course to dodge a single object, because the actual average distance between one asteroid and its nearest neighbor out there is closer to 1 million miles. You could drift through the real asteroid belt for years, in any direction, and never come near one, let alone need to dodge it. Every asteroid field chase scene you've ever watched in a theater was staged in a belt that has never existed anywhere in this solar system. No planet broke apart to make that belt. A planet simply never got permission to finish. And the gap between the crowded belt Hollywood built and the almost empty one actually orbiting out there is worth carrying into what comes next. Because the next mistake isn't about somewhere too crowded. It's about somewhere everyone assumes is perfectly, completely empty, and isn't. Jupiter's interference with the asteroid belt didn't stop at preventing a planet from forming. Look at a map of where asteroids actually sit today. plotted by distance from the Sun, and the belt isn't evenly scattered rubble at all. It has gaps in it, sharp, specific, nearly empty lanes at exact distances, first mapped by the American astronomer Daniel Kirkwood in 1866, and still carrying his name. The gaps sit at distances where an asteroid's orbital period would land in a clean ratio with Jupiter's own orbit. 3 trips around the Sun for every one of Jupiter's, or 5 for every 2, or 7 for every 3. An asteroid unlucky enough to settle into one of those precise ratios gets tugged by Jupiter's gravity at the exact same point in its orbit, over and over. Every single lap, instead of receiving that tug at random, ever-changing angles the way most asteroids do. Random tugs cancel each other out over time. Repeated tugs at the same point in an orbit add up, compounding lap after lap, until the asteroid's path gets stretched into something unstable enough to send it flying out of the gap entirely, either deeper into the solar system or out of the belt altogether. Jupiter, it turns out, isn't just an old bully that stopped a planet from forming billions of years ago. It's still actively landscaping the belt today, mile by mile, maintaining specific empty lanes through gravity alone, with no engineer and no plan, just the same relentless arithmetic that keeps every other correction in this episode running exactly on schedule. Kirkwood found these gaps in 1866, using nothing more advanced than pencil, paper, and a catalogue of the asteroids known at the time. Fewer than 100 of them, compared to the roughly 1 million catalogued today. He didn't have a telescope sensitive enough to watch a single asteroid get ejected from a resonant lane in real time. He had a list of orbital periods, a lot of patience, and the observation that certain periods were suspiciously, consistently missing from the list, over and over, no matter how many new asteroids got added to it. Picture a swing set and someone pushing a child on it at exactly the wrong moment in every cycle, again and again, timed perfectly wrong instead of perfectly right. A push timed to match the swing's own rhythm builds it higher and higher. A resonant orbit works the same way, except the repeated nudge from Jupiter doesn't build height. It builds instability, tightening the same imperfection lap after lap until the orbit itself can no longer hold together in that lane. You don't need a large force to wreck something over geologic time. You just need the same small, badly timed push, applied at the same exact point for a few million years running. The largest of these lanes, sitting at the point where an asteroid would orbit exactly 3 times for every 1 Jupiter completes, is nearly empty enough today to be visible on a simple chart of the belt's structure, a clean dark stripe cutting through an otherwise scattered field of dots. Nobody had to remove anything from that stripe. Jupiter simply made sure nothing that ever wandered in stayed for long enough to matter, patiently, for longer than any planet has existed with a name attached to it. Take 2 uncharged metal plates, polished perfectly flat, and seal them inside a chamber, with every last molecule of air pumped carefully out. A true vacuum, as close to completely, totally empty as any laboratory can build. Push the 2 plates to within a very small fraction of a hair's width of each other, close enough that almost nothing at all should exist in the gap between them. And something strange happens anyway. The plates pull toward each other, not because of any charge, any leftover gas, any wire connecting them. Something present in the emptiness itself, with nothing visible inside it at all, is steadily shoving the 2 plates together. The Dutch physicist Hendrik Casimir predicted exactly this in 1948, and it took nearly 50 years for an experiment precise enough to confirm the force he calculated. The American physicist Steve Lamoro finally measured it directly in 1997, matching Casimir's prediction to within about 5%. The explanation has nothing to do with the plates, and everything to do with what empty space actually contains. According to quantum field theory, a true vacuum is never perfectly still. It's a constant, chaotic froth of particles, and their antiparticles blinking into existence in pairs and vanishing again almost immediately, borrowing the energy to exist for a moment so brief no instrument could ever catch one directly. A debt so impossibly short-lived that the universe's own accounting rules, built directly into the uncertainty principle itself, allow it to go completely, permanently unpaid. Squeeze two plates close enough together, and you restrict which of those flickering pairs have room to exist in the gap between them. Fewer of them fit inside than outside, which means slightly less of that background froth is pushing outward from the middle than is pushing inward from beyond the plates. The imbalance is small. It is also completely real, measured in a lab, using two pieces of metal and nothing else. Here's what that does to the word empty. Every patch of space you have ever looked at, the air over your head right now, the true vacuum between galaxies, the gap between two fingers held an inch apart, is doing this, constantly. Whether anything is there to measure it or not, you will never feel the Casimir force yourself. It only becomes measurable at a scale close to a millionth of a meter, far too faint to register against gravity or friction on anything the size of a hand. But engineers building the tiniest machines humans have ever manufactured. Sensors and switches built at that same microscopic scale, thinner than a human hair, run into it constantly and unglamorously as an actual design problem. Components meant to move freely, sometimes stick together permanently, welded shut, not by heat or static, but by empty space itself, pressing two surfaces close enough to activate a force that isn't supposed to exist between things with nothing between them. Nature's smallest fingerprint shows up first as an inconvenience on a factory floor, filed under mechanical failure long before anyone thinks to blame the vacuum. Physicists have a specific name for what's flickering inside that vacuum. Virtual particles, pairs of matter and antimatter that borrow enough energy from empty space to exist for the barest instant before annihilating each other and returning that borrowed energy, as if the transaction had never happened at all. It sounds like a loophole, and in a very real sense, it is one, written directly into the mathematics of the Heisenberg uncertainty principle, which says that energy and time can never both be perfectly nailed down at once. Borrow a large enough amount of energy, and the universe allows it, as long as you pay it back fast enough that nobody outside the transaction ever gets to observe the debt directly. You cannot see this happening directly, not with any instrument built so far, and probably not with any instrument that will ever be built by anyone. What you can see instead are the consequences it leaves behind. The Casimir force between two plates, and something even stranger at the edge of a black hole, where one particle of a virtual pair can fall in while its partner escapes outward, turning a transaction that was never supposed to be observed into something that permanently leaves the scene. Stephen Hawking worked out that consequence in 1974, and it broke an assumption that had survived every other correction so far tonight, that black holes are permanent. If one particle from a borrowed pair can escape while the other falls in, then a black hole is very slowly radiating real energy outward at the expense of its own mass, particle pair by particle pair, for as long as it exists. Every black hole in the universe is evaporating, slowly enough that none has fully disappeared since the universe began, but not slowly enough to call it permanent anymore. Sit with what that actually implies. Before 1974, a black hole was treated as physics' one true dead end, a place where matter went and simply stopped being part of the story. Hawking's insight turned every single one of them into an object with a lifespan, however long, ticking down at a rate so faint that a black hole the mass of a star would take vastly longer than the current age of the universe to fully evaporate. You will never witness one disappear. Nothing alive today ever will. But for the first time, the phrase, "nothing escapes a black hole," stopped being completely true, decades before most textbooks caught up to the correction. The mechanism is quieter than the popular version too. Nothing is reaching inside the black hole and pulling a particle out. The split simply happens to occur near enough to the boundary that one half of a flickering pair has room to escape before the debt comes due, while its partner doesn't. Empty space, doing exactly what it does everywhere else in the universe, above your head right now included. Just close enough to a boundary this time that the bookkeeping doesn't balance. Now add the number that turned this from an elegant curiosity into one of the strangest unsolved problems in physics. If empty space really is filled with these flickering particle pairs, then a vacuum shouldn't just push on metal plates. It should carry energy of its own, a background hum, present everywhere. In every cubic inch of space, whether a single atom occupies it or not. Physicists can calculate roughly how much energy that vacuum hum should carry, using the same quantum field theory that predicted the Casimir force correctly. The number that calculation actually produces is, by some estimates, roughly 10 million trillion 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 times larger than the amount of vacuum energy astronomers can actually measure by carefully watching the universe expand. Physicists studying this specific mismatch have openly called it the worst prediction in the entire history of science, and by every honest measure available to them, they are not exaggerating even slightly. Every other prediction quantum theory has ever made checks out to a dozen decimal places. This one misses by more decimal places than most people will ever see written out in a single number. Here's how astronomers actually caught the real value. And it wasn't by measuring the vacuum directly. In 1998, two separate teams of astronomers were watching a specific, reliable kind of exploding star called a Type Ia supernova, using its known, reliable brightness the way a lighthouse of a known wattage lets a sailor calculate distance from shore in total darkness. Both teams expected to confirm that the universe's expansion, set in motion by the Big Bang, was gradually slowing down under its own gravity, the way a ball thrown upwards slows as it climbs. Both teams, working independently and half expecting to simply confirm each other, found the exact opposite. The most distant supernovae were dimmer than they should have been if the expansion were merely coasting, which meant they were farther away than expected, which meant the expansion of the universe itself was accelerating, not slowing. Something invisible was pushing space itself apart, harder over time, against the combined gravitational pull of every galaxy in existence. You were taught, if you were taught this at all, that gravity is the only force running the universe at the largest scales, pulling galaxies together, slowing the expansion, eventually maybe reversing it. The 1998 discovery broke that completely, and the physicists who led the two teams shared a Nobel Prize in 2011 for measuring it. Astronomers gave the mysterious pushing force a name they openly admit is a placeholder for their own ignorance: dark energy. Nobody has solved what it actually is. Tonight will not solve it either, but hold on to that mismatched number from a few minutes ago, because before this episode ends, it's going to come back under this new name. And it's going to turn out to explain roughly 95% of everything that exists, hiding in plain sight in every single measurement astronomers have taken since. You already heard this exact number at the very start of tonight, stated completely flat, without any hedging language attached to it at all. Replace the Sun with a black hole of the exact same mass, and Earth's orbit does not shift by one measurable second. Here is why that isn't simply a trick of phrasing. Gravity, at any distance greater than an object's own physical size, only ever cares about two specific things: how much mass is actually sitting there, and how far away you happen to be from it, not what that mass looks like. Not whether it has a solid surface, a churning atmosphere, or no surface at all. The Sun and a black hole built from the exact same amount of matter would pull on Earth with identical strength at Earth's actual distance, because gravity at that range has no way of telling the two apart. Compressing the Sun down to a black hole wouldn't concentrate its pull. It would only shrink the boundary at which its existing pull becomes inescapable. A boundary that, for a mass like the Sun's, would sit a little under 2 miles from the center. Earth orbits 93 million miles out. From that distance, nothing about the planet's yearly path would notice the difference for a single second. The clearest proof of this isn't a thought experiment. It's sitting at the center of the Milky Way, roughly 26,000 light-years away, where a black hole with a mass around 4 million times the Sun's has been tracked in real time by astronomers for more than 2 decades. A star called S. 2 orbits that black hole on a normal, predictable ellipse, obeying the same gravitational rules that keep Earth orbiting the Sunday. Not being reeled in by any special suction, just following ordinary gravity around an object massive enough to bend space steeply, the same way every mass in this episode has bent space so far. 2 astronomers, Reinhard Genzel and Andrea Ghez, spent decades independently tracking S2's path across the sky, using 2 different telescopes on 2 different continents, refining the orbit year after year until the shape of it left no reasonable doubt about what was sitting, unseen, at the center of that ellipse. Their work earned them a share of the 2020 Nobel Prize in Physics, not for detecting some exotic new force reaching out from the galactic center, but for confirming that an ordinary, if extraordinarily massive, gravitational source was sitting exactly where the math said it had to be, pulling on a nearby star with nothing more exotic than mass and distance. So the word sucks, the one used in almost every casual description of a black hole, is wrong at any distance where it would actually matter to you. A black hole doesn't reach out any farther or pull any harder than an ordinary star of the same mass sitting in the same spot, watched from the same safe distance. What changes isn't the pull. It's how close you're allowed to get before something else entirely takes over. Here's the part the word sucking actually gets wrong. Gravity near any massive object grows stronger the closer you get to it. That's true of Earth, true of the Sun, true of anything with mass. Stand at the Sun's actual surface, and its gravity is already about 28 times what you feel standing on Earth. A black hole doesn't invent a new kind of pull. It simply removes the flaw. There is no solid surface to stop you at a safe distance the way the Sun's surface stops anything from falling deeper into it. The only thing waiting past a black hole's edge is more of the same gravity, growing stronger, with nothing solid left to interrupt the fall. That edge has a name: the event horizon. And it isn't a wall, a membrane, or a surface of any kind. It's simply the distance at which gravity has grown strong enough that escaping would require moving faster than light, which nothing in this universe is able to do. Cross it, and you haven't collided with anything, haven't triggered anything, haven't felt a single sensation change. You've just run out of any possible path, in any direction, that leads back out. You could, in theory, cross a large enough black hole's horizon without a single instrument on board registering anything unusual at that exact moment. There's no flash, no wall, no sudden jolt marking the boundary, only the slow, growing realization, if there were time left to realize anything. Get close enough before that point, and gravity stops treating your body as a single object. The pull on the part of you closest to the black hole becomes measurably, then catastrophically, stronger than the pull on the part of you farthest away. A difference too small to feel standing on a planet, but violent enough near a small enough black hole to stretch a falling object into a thin strand of matter. A process physicists actually call, without much poetry, spaghettification. A structural failure stretched out over the last seconds anything gets to have. Here's the twist almost nobody expects, and the last correction to this particular myth. Bigger black holes are actually gentler at the boundary, not worse. The stretching force depends on how sharply gravity's strength changes over the length of your body, and for a small black hole, just a few times the Sun's mass. That change happens brutally fast, tearing anything apart long before it reaches the horizon. For a supermassive black hole, the kind sitting at the center of a galaxy, the horizon itself is so enormous that gravity barely changes at all across the length of a human body while crossing it. You could, in principle, fall through the boundary of a large enough black hole feeling nothing unusual at all, and only meet the violence much later, deeper inside, on the way to the center. Size doesn't just change the danger. It changes exactly when the danger arrives. Remember the disagreement between two clocks a few feet apart, and the promise that it would eventually be measured in years instead of millionths of a second. Here is where that promise gets paid, and it undersold, by a wide margin, what actually happens. Every single clock mentioned in this episode so far has disagreed with every other clock by some finite, measurable amount. 38 microseconds a day for a satellite, a fraction of a second over a lifetime for someone standing on a slightly higher shelf. A black hole is the one place in this universe where that pattern breaks completely. Not because the mechanism changes, but because gravity finally grows strong enough to push the disagreement all the way to its logical extreme. Picture someone falling feet first toward a black hole while you watch from a safe distance through a telescope. From where you're standing, they never quite arrive. As they approach the event horizon, the same gravity that's stretching their body is also stretching the light, leaving it, shifting it toward the red end of the spectrum, and slowing the rate at which each successive image reaches you. Their fall appears to slow, then crawl, then stop, frozen at the edge, fading redder and dimmer, for what would be, from your side of the telescope, an amount of time with no upper limit at all. Not years, not centuries, as far as any outside observer could ever measure. Forever, from the falling person's own perspective, none of that happens. Their fall continues perfectly normally on a clock that feels completely ordinary and unremarkable to them, crossing the horizon in an unremarkable instant and reaching the center in a span of time that, for a black hole the mass of the one at the center of this galaxy, would be measured in minutes. This isn't only a thought experiment either. In 2018, a team of astronomers using an instrument called gravity watched that same star, S2, swing through the closest point of its orbit around the black hole at the center of the Milky Way. Close enough, moving fast enough, that its own light measurably reddened exactly the way gravitational time dilation predicted, the same stretching effect happening on an almost unimaginably gentler scale to a clock a few feet off your own floor. A star, its actual light, arriving redder than it left, because time itself had genuinely passed differently for it than it did for the astronomers reading the signal at their desks. Two separate clocks, watching the exact same physical event unfold from two different vantage points, disagreeing completely about whether it happened quickly or whether it never actually finished at all, and both of them, according to every equation physicists currently have, are simultaneously fully correct, not a paradox, waiting patiently to be resolved by some future theory. Just what gravity actually does to time, laid bare at a scale finally large enough for a telescope on Earth to catch it happening, decades after Einstein first wrote the mechanism down on paper. The Milky Way is usually pictured as a finished object, a settled spiral, its arms fixed in place, its shape decided billions of years ago and left unchanged ever since. Look closely at the actual motion of its individual stars, though, and that tidy picture falls apart almost immediately. The galaxy you have lived inside your entire life is still being built out of pieces that used to belong to somebody else entirely. The clearest evidence is written into the paths stars take through the galactic halo, the faint outer sphere of stars surrounding the Milky Way's disk. In 2018, data from the European Space Agency's Gaia spacecraft, a satellite built specifically to measure the precise position and motion of more than 1 billion individual stars, revealed that a huge number of halo stars share an unusual, elongated, sausage-shaped pattern of motion, all moving as if they had fallen into the galaxy together, from the same direction at roughly the same distant point in time. Astronomers eventually gave the event a fairly modest name that undersells how genuinely large it actually was: Gaia Enceladus, a separate galaxy carrying roughly as much mass as several hundred million suns that collided with the young Milky Way somewhere between 8 and 11 billion years ago and never left. Its stars didn't simply vanish, and they didn't get destroyed in the impact the way two solid physical objects might shatter violently on collision. They simply joined the crowd, settling into new orbits that, over billions of years, built much of the thick disk and inner halo you're technically standing inside right now. Indistinguishable today, star by individual star, from stars the Milky Way supposedly built for itself from scratch. Before Gaia's survey, astronomers already suspected something like this had happened. Stellar populations in the halo were oddly diverse. Some stars chemically younger, some older, moving on paths too eccentric to make sense for a galaxy that had simply formed once and settled down quietly ever since. What Gaia added was precision. Not a hint buried in noisy data, but the actual shape of an entire cannibalized galaxy, traced star by star, sausage-shaped orbit by sausage-shaped orbit, sitting in plain sight the whole time, waiting for an instrument sensitive enough to notice the pattern. Some of those Gaia Enceladus stars are close enough and bright enough that you have almost certainly already seen one with your own eyes on a clear night without ever knowing it. No different in appearance, brightness, or color from any star actually born inside the Milky Way, carrying no visible label marking where it actually came from originally. The galaxy you were taught to think of as a single, coherent thing is, at the level of individual points of light, a very old crime scene that nobody bothered to clean up because there was never anything wrong with leaving the evidence in plain sight. That merger wasn't the last one, and it isn't even finished being the most recent one. In 1994, astronomers finally found a small galaxy. A few 100 million stars, tiny by galactic standards, orbiting so close to the Milky Way's own center that it had gone completely unnoticed for decades, hidden behind the glow of our own galaxy's densely crowded core. They named it, plainly, the Sagittarius Dwarf Galaxy. And the reason it took astronomers so long to actually find wasn't distance. It was proximity. The Milky Way's own gravity has already pulled it in tight enough that it completes a full orbit in roughly 1 billion years, repeatedly punching straight through the galactic disk on each and every close pass. Every single one of those repeated passes costs it more stars than the last. Tidal forces the same basic stretching effect that pulls a falling body towards spaghettification near a black hole, just gentler, slower, and running on a galactic clock instead of a human one, have been peeling material off the Sagittarius dwarf for billions of years now, drawing it into a long, thin ribbon of stars that now wraps most of the way around the entire Milky Way, looping over the galactic poles rather than lying flat in the disk. Astronomers simply call it the Sagittarius Stream today, and it isn't some hidden or purely theoretical structure. It's visible today, mapped star by star across multiple wide-field surveys built specifically to trace it, an actual ribbon of stolen starlight draped across the sky. What's left of the dwarf galaxy itself? The dense core that hasn't yet been fully unraveled into the stream is still down there, still orbiting, still losing a little more of itself on every single pass through the disk. Current estimates give it perhaps another few billion years left before there's nothing dense enough remaining to honestly call it a separate galaxy at all anymore. It will simply finish becoming part of the Milky Way, the same way Gaia Enceladus already did, one stripped away star at a time, on a timeline too slow for you to ever perceive the process moving. Here's the detail that tends to surprise people who assume mergers like this are rare cosmic accidents. They aren't. Almost every large galaxy astronomers have studied carefully shows the same kind of evidence. Streams, shells, oddly clustered stellar populations, left behind by some earlier meal, building a galaxy this size, this old, without eating several smaller ones along the way, turns out to be the genuinely unusual outcome, not the normal one, in every serious survey astronomers have run so far. Now add what that actually means for the shape you've been picturing all along. The Milky Way isn't a static spiral with a stream of tidy debris politely orbiting outside it. It's a galaxy actively consuming a smaller one. Mid-meal, close enough that some of the Sagittarius dwarf stars have almost certainly already passed through the same neighborhood of the galaxy your solar system currently occupies. Unnoticed, indistinguishable by eye from stars that were always yours. Which finally explains why the most famous galactic collision of all, the one between the Milky Way and the Andromeda Galaxy, expected in roughly 4.5 billion years, isn't the catastrophe most breathless descriptions make it sound like, and never was, from the very first calculation. If you've heard about this collision at all, you've probably heard it described with words borrowed from a car crash. Impact, destruction, obliteration. None of those words survive contact with how much truly empty space actually separates one star from the next. Picture two swarms of bees, each one enormous, drifting toward each other from a distance. Fly close enough to watch what actually happens where the swarms meet, and the individual bees mostly pass each other by because the empty space between any two of them is enormous compared to how small each one actually is. Stars work the same way, at a scale that makes a swarm of bees look packed shoulder to shoulder by comparison. The average distance separating two neighboring stars is trillions of miles, meaning a single star is, proportionally speaking, far smaller relative to the emptiness surrounding it than one bee is relative to an entire swarm's open air. Astronomers who've modeled the coming collision in detail, using real telescope data on both galaxies' mass and structure, put the odds of the Sun itself ever physically colliding with another star during the entire hundreds of millions of years long merger at close to zero. Not negligible in the casual sense people use that word, but the kind of number where essentially never happens is the honest, technical, peer-reviewed answer. Astronomers have run these simulations more than once, refining them as better telescope data on both galaxies' true mass and trajectory came in, and the answer has held steady every time. Essentially 0 stellar collisions across a merger involving roughly 1 trillion stars combined. What will actually happen instead is stranger and slower than any collision. 2 spiral galaxies will pass through each other, mostly empty space sliding through mostly empty space, while gravity flings stars onto new, wilder orbits over hundreds of millions of years. The tidy spiral shape both galaxies currently wear will eventually be replaced by a single, larger, far more shapeless galaxy that astronomers have already given a working nickname, half joking and half serious. Milkomeda. No planet destroyed anywhere in the process. No star so much as grazed, let alone struck directly. Just a slow, patient rearrangement of 2 galaxies that have technically already started falling toward each other right now. While you listen to this very sentence at a speed too small to ever notice in a single human lifetime, what might actually change over that unimaginable stretch of time is something quieter and stranger than destruction: the sky itself. Long before any merger completes, Andromeda will grow from a faint smudge into a second visible spiral stretched across the night, filling more and more of the view above whatever is left to look up from Earth by then. Nobody alive today will ever see it. But something, someday, might. Andromeda gets all the attention, largely because it's the one bright enough to see with the naked eye on a dark night. It isn't actually next in line. The Large Magellanic Cloud, a small satellite galaxy currently orbiting the Milky Way at a fraction of Andromeda's distance, is already close enough and losing orbital energy fast enough that a research team modeling its trajectory in detail in 2019 put its merger with the Milky Way at roughly 2.5 billion years from now, well over 1 billion years before Andromeda even arrives on schedule. It's smaller than Andromeda by a wide margin. Currently visible from the southern hemisphere as a faint smudge of its own, and it's already close enough that the Milky Way's gravity is actively stripping gas out of it. The same slow theft currently happening to the Sagittarius dwarf. Add this to tonight's running total, and the Milky Way isn't simply waiting around for one distant, headline-grabbing collision in the far future. It's mid-conversation with at least 3 separate galaxies at once, on 3 completely different timelines, absorbing one, stretching a second into a stream, and slowly reeling in a third. An entirely ordinary Tuesday at galactic scale. You've almost certainly seen the large Magellanic Cloud without knowing what it was if you've ever spent a clear night far enough south of the equator. It looks, to the naked eye, like a small detached piece of the Milky Way's own hazy band, a stray patch that simply drifted a short distance away from the rest of it, which is close to the literal truth of what's about to happen to it, just running in the opposite direction from what the eye suggests. Rather than drifting further away, it's spiraling steadily closer, caught in an orbit that's already decaying. The 2019 study that modeled its coming merger, led by researchers using detailed measurements of the cloud's mass and trajectory, found something else worth sitting with. A galaxy this size carries enough of its own dark matter halo that its arrival could disturb the orbits of stars throughout the Milky Way, including, potentially, stars much closer to home than anyone watching from Earth might expect. Long before any visible collision, the smaller galaxy's gravity will already be rearranging furniture in a house it hasn't technically entered yet. There's a strange comfort tucked inside how ordinary all of this turns out to be. Once the fear movie framing gets stripped away, a galaxy isn't a fortress under siege from outside. It's closer to a slow, patient household, constantly absorbing smaller relatives, constantly losing a little material to a larger neighbor's pull, on timelines too long for any single generation to watch, start, and finish. The Milky Way you were born under has already changed shape more times than anyone alive will ever be able to count firsthand, and it will keep doing so, calmly, patiently, long after every single star currently visible from Earth tonight has gone dark. Picture the Big Bang, the way almost every documentary, textbook diagram, and casual conversation pictures it. An explosion, a single brilliant point somewhere in the darkness, matter hurling outward into the empty space surrounding it. The way a firework detonates and scatters sparks into the night sky around it. That image is wrong in a way that isn't a minor technical correction. It's wrong about the single most basic fact in the entire scenario: where it happened. There was no empty space out there for anything to explode into. Space itself did not exist yet, waiting patiently somewhere in the dark to receive an explosion arriving from a different location. What cosmologists actually mean by the phrase Big Bang is that space itself began expanding, everywhere, simultaneously, with no outside region for that expansion to be happening inside of. Not a bomb going off in a room. The room itself, coming into being and stretching, with nothing beyond its own walls for the stretching to expand toward. This is, by a wide margin, the single most common misunderstanding about the origin of the universe. And it isn't a failure of imagination on anyone's part. Every explosion a human being has ever witnessed, a firework, a car crash, a bomb on the news, happens inside space that was already there beforehand, waiting to receive the blast. Nothing in ordinary experience prepares a person to picture an explosion that includes the room itself as part of what's being created. The comparison was never a small simplification. It smuggled in a false answer to the very first question anyone asks. Where? Here's the sentence that tends to break people's mental picture completely. There is no location in the universe today that you could travel to and call the site of the Big Bang, the way you could travel to the site of an actual explosion on Earth and stand in the crater it left behind. Every point in the universe, including the exact point of space you are occupying right now, was equally present at the beginning, because there was never any elsewhere for any single point to have started, apart from all the others. Astronomers get asked, more than almost any other question about the universe, to point in some direction and say that's where it happened. There is no honest answer to give them, and not because the true location simply hasn't been found yet with a good enough telescope. The question itself quietly assumes a kind of geography. An inside and an outside, a here and a there, a before you arrive and an after. That flatly did not apply at the actual moment space itself first began. You are not located some measurable distance away from the Big Bang. The way a house sits a certain distance from a fire that burned down the street years ago. You are standing inside the aftermath of it, everywhere you have ever physically been in your entire life. Because the aftermath is what space itself, in its entirety, turned out to actually be. The usual fix for that broken mental picture is a balloon. Draw dots on the surface of a balloon to represent galaxies, inflate it, and watch every dot move away from every other dot at once. No single dot sliding toward the center of the balloon because the surface itself is what's stretching. It's a genuinely useful image, and almost every popular explanation of the Big Bang reaches for it. It also breaks down in exactly the place most explanations stop talking, which is worth naming instead of skipping past. A balloon's surface is two-dimensional, and it's expanding into the three-dimensional room around it. A room you, watching from outside the rubber, can actually see with your own eyes, holding the balloon in your own hands. That's precisely the part of the picture cosmologists need you to unlearn. The universe isn't a three-dimensional surface expanding into some larger fourth-dimensional room that a bigger observer, standing somewhere else, could watch from outside. As far as any evidence has ever shown, in over a century of trying to find one, there is no outside. The expansion isn't happening inside a larger container that existed first. The container itself, if that word even honestly applies anymore, is the very thing doing the expanding. Physicists have built better analogies since, ones that drop the extra dimension entirely, stretching a rubber sheet in every direction at once with no edge to run off of, or simply doing the math without a picture at all, since the equations never needed a container to begin with. Human intuition, built entirely inside a universe that already has insides and outsides everywhere it happens to look, is the part still struggling to keep up. The mathematics settled this question decades before most people's imagination caught up to it. Here's where the evidence stops being a thought experiment and starts being something you could, in principle, point an instrument at yourself. Point a sensitive enough receiver in any direction at all, not one preferred direction, every direction, equally, straight up or straight down or anywhere between, and you find the same faint ancient microwave glow left over from the universe's early heat, sitting at nearly the same temperature no matter which way the instrument happens to be aimed. If the Big Bang had actually happened at some specific location out there, that glow should logically be brighter, or older, or somehow different in the direction of the true origin point, and fainter or younger everywhere else. The way heat fades as you walk away from a campfire. It isn't. It's the same in every direction, to a precision better than 1 part in 100,000. Measured repeatedly by multiple independent instruments over decades. That's exactly what you'd expect to find if there had never been a single point of origin left to look back toward in the first place. And it's very close to the last result anyone would expect from a genuine, one-location explosion. That uniform microwave glow from every direction creates a second problem the moment you actually think through the geometry of it. One most explanations skip entirely. Look at that ancient light arriving from directly overhead, then look at the same ancient light arriving from the exact opposite direction, and both signals have been traveling toward you for the entire age of the universe. Given how fast light travels, and how old the universe actually is, those two opposite patches of sky should never have been able to exchange so much as a single photon of heat with each other. They're too far apart, and the universe hasn't existed long enough for anything, light included, to have crossed that distance and evened out the temperature between them, and yet they match to a precision better than 1 part in 100,000, as if they'd spent plenty of time sitting right next to each other sharing heat back and forth until the temperature settled evenly. Cosmologists call this the horizon problem. And the leading explanation carries a word that undersells exactly how strange it actually is. Inflation. The physicist Alan Guth proposed in 1980 that in a fraction of a second after the universe began, a span of time too short for a number to feel meaningful describing it, space itself underwent an almost unimaginably rapid burst of expansion, stretching a tiny patch of already uniform, already connected material into a region larger than anything light could cross again for billions of years afterward. Those opposite patches of sky match because they were never actually far apart to begin with. They started right next to each other, already at the same temperature, before space itself yanked them to opposite sides of the observable universe, faster than anything could carry the memory of that shared heat back and forth again. The scale of that early stretching is difficult to render honestly, without sounding like exaggeration for effect. So consider the actual figure some models put forward: a patch of space smaller than a single atom, expanding by a factor of something like a trillion times over, in less time than it takes a single beam of light to cross that original atom-sized patch. Ordinary expansion, the gentle kind still stretching a comet's tail and a galaxy's light tonight, never moves anywhere near that fast. Inflation, if the theory is correct, was a completely different regime of physics, operating for the barest possible sliver of the universe's first, second, and then switching off, leaving the much gentler expansion measured ever since as the only remaining evidence it ever happened at all. No instrument has directly detected inflation itself, the way gravity detected a star's light bending, or the way a rotation curve directly measured dark matter's pull. The evidence is entirely indirect. A uniform temperature that shouldn't exist without it. A geometry of space that comes out remarkably flat in every survey astronomers have run. Exactly the way inflation predicts, and nothing else quite manages to explain as cleanly. An idea that solved a problem so thoroughly that most cosmologists accepted it years before anyone found a way to test it directly, which finally explains something that sounds like a technicality and isn't one. Why astronomers are careful to say galaxies are moving away from each other and reluctant to say they're moving through space to do it. When a car drives away from you, the sound of its engine stretches to a lower pitch, the ordinary Doppler effect, caused by the car physically moving through the air, separating you from it. For decades, the retreat of distant galaxies was described using the exact same language. Light stretched to redder wavelengths because the galaxies were racing away from us through space. That description works well enough at short distances. At the scale of the whole observable universe, it stops being accurate, and the difference matters. Most of the redshift astronomers measure in distant galaxies isn't caused by anything physically moving through space at all. It's caused by space itself stretching during the time it took that light to travel from its source all the way to your eye, the light's own wavelength expanding right along with the universe carrying it. The same way a wavy line drawn on that same balloon's surface stretches longer as the balloon inflates, without the line itself crawling anywhere across the rubber underneath it. The galaxy on the other end isn't fleeing anywhere. The distance between here and there is simply getting larger. On its own, while both ends sit essentially still, relative to the small patch of space immediately around each of them. This is also why the most distant galaxies astronomers can detect appear to be retreating faster than the speed of light. A sentence that sounds like it violates physics and doesn't. Nothing is moving through space faster than light. Space itself, over a distance large enough, is simply stretching fast enough that the gap between here and there grows at a rate light can't keep pace with. A loophole that exists only because the speed limit governs motion through space, not the growth of space itself. Now hold both corrections at once, because they're really the same correction, wearing two different names. Nothing exploded into an emptiness that was already sitting there beforehand, and nothing out there is truly fleeing from you through some fixed, unmoving cosmic backdrop. Space itself is doing both jobs, being born everywhere, all at once, and then steadily widening every gap it holds ever since, from the distance between two entire galaxies down to the distance growing, ever so slightly, between the Earth and its own moon. 4 corrections into this half of tonight alone, and every single one has traced back to the same underlying idea. Distance, direction, and location only work the simple way you were taught inside a box, small enough to hold perfectly still. Step outside that box. A comet, a falling body, a galaxy, the origin of the universe itself, and here and there stop being reliable words to build an explanation on. What's left standing, once they're gone, is the strangest correction still waiting tonight. How much of everything actually filling that space has never once been directly seen by anyone at all. Here's a number people who already know the universe is 13.8 billion years old tend to get wrong immediately afterward. If the universe is 13.8 billion years old, the observable universe must be a sphere, 13.8 billion light-years in radius, since light can only have traveled that far since the very beginning of everything. It's a clean, perfectly reasonable piece of arithmetic, the kind you could work out on the back of a napkin without a single mistake in the math itself. It's also off by more than a factor of 3, and the reason why is the same correction this entire episode has been quietly circling since the opening minute, dressed up in a new costume. Distance and light travel time only match up cleanly in a universe standing still. The same way 1 year only meant one clean, simple thing back before you learned, the sun itself refuses to hold still while carrying you around it. Light left the most distant visible galaxies roughly 13.8 billion years ago. That part is correct, but the space between here and those galaxies has been expanding for that entire 13.8 billion years, stretching the distance between you and that ancient light for the whole time it was traveling toward you. By the time that light finally reaches a telescope tonight, the galaxy that originally sent it isn't 13.8 billion light-years away anymore. It's approximately 46.5 billion light-years away, carried outward the whole time by the same expansion of space that's been stretching every distance in this episode, from a comet's tail to the wavelength of that very light arriving in the instrument. Run that number both directions, and the picture gets stranger. The observable universe isn't a 13.8 billion light-year sphere centered on Earth. It's roughly 93 billion light-years across, edge to edge, and every figure in that sentence is a live, moving target, rather than a fixed boundary painted onto the sky once and left alone. The boundary keeps receding, the light keeps arriving late, and the number cosmologists quote keeps growing larger with each new year of observation. Not because the universe is expanding into more universe that wasn't there before, but because more of the light that was always in transit finally has time to complete the trip and arrive. You were taught the age of the universe as a single clean fact, and it is one. You were probably never taught that the size of the observable universe isn't simply that age multiplied by the speed of light, the way it would be for absolutely anything else in ordinary life, with a known age and a known constant speed. Space itself, the entire time that light was in flight toward you, was steadily cheating the arithmetic in its own favor, adding extra distance to the trip after the light had already departed. Astronomers have a specific name for the more honest number, separate from the simple age times speed guess. The comoving distance, a figure that accounts for every mile of expansion added to the road after the light already set out on its journey. It's the number that actually determines what you could, in principle, reach someday, given enough time and a fast enough ship, rather than the far smaller number that only describes how old the light happens to be by the time it finally arrives. Even professional astronomers occasionally catch themselves quoting the wrong figure in casual conversation, reaching for the simple age-based number out of habit before correcting themselves mid-sentence. It's a completely understandable mistake to make, precisely because the wrong number is the one that matches ordinary human experience of distance and time everywhere else in life. The only place in the universe where that intuition actually breaks down is at the very largest scales it was never built to handle. Here's the correction inside the correction. The one that tends to unsettle people far more than the number itself ever does. Observable universe was never meant as a description of how big the universe actually is. It's a description of how far light has managed to reach you so far, which turns out to be an entirely different, much smaller, far more modest question than the one most people think they're asking. Think about what the word observable is actually admitting. Right there, in plain sight. It isn't claiming to describe the universe. It's describing the limits of your own particular vantage point, sitting on one ordinary planet, orbiting one ordinary star, looking outward for exactly as long as light has had to reach that specific spot. Move the vantage point even a modest distance, and the entire observable sphere shifts to center on that new location instead, no matter where in the universe it happens to sit. Astronomers on a planet orbiting some galaxy 40 billion light-years from here would have their own 9 billion light-year sphere, centered entirely on themselves, overlapping only partly with the one centered on you. The universe itself never moves a single inch to accommodate anybody's particular view of it. Every observer simply gets handed their own private, honest slice of the whole. Nothing about physics suggests the universe stops existing at that 9 billion light-year boundary, the way a room stops existing at its own walls. Most cosmologists studying the geometry and large-scale structure of the observable region conclude the actual universe almost certainly continues well past it, plausibly hundreds of times larger than what's visible, possibly infinite in extent, filled with more galaxies, more stars, more of everything already described tonight, existing in complete, permanent silence as far as you personally will ever be concerned. That particular silence isn't the ordinary kind, the familiar kind that distance alone tends to create. A ship sailing over the curve of the ocean horizon disappears from view, but it hasn't stopped existing, and it could, in principle, turn around and sail back into sight. What separates you from the rest of the universe is closer to a genuine law of nature than a matter of distance. The light from those far places has simply not had time to reach you yet, and thanks to the accelerating expansion discovered back in 1998. The same discovery that first put a number on dark energy. An enormous share of that light now never will. It's receding away from you faster than its own light can ever close the gap, permanently, no matter how much time is allowed to pass. You will live out an entire complete life, start to finish, and so will every single person who has ever been born or who will ever be born after you, without one single verified fact ever arriving from most of what actually, factually exists out there. Not because nobody built a strong enough telescope, and not because anyone gave up looking too soon, because the universe itself, expanding the whole time nobody happened to be watching, made absolutely certain the message could never physically complete the trip. There's a second boundary hiding behind the observable universe's edge, one astronomers rarely mention in the same breath, and it's a stricter, sadder line than the first. The observable universe describes everything whose light has already reached you. This second boundary describes something worse. The point beyond which light leaving right now will never reach you at all, no matter how much time is allowed to pass. Astronomers call it the cosmic event horizon, and the name isn't a coincidence. It works on the same basic principle as the black hole boundary from earlier tonight, just stretched across the entire universe instead of a single collapsed star, because the expansion of space is accelerating, driven by that same unexplained dark energy. A galaxy far enough away is currently receding from you faster than light can close the gap between here and there. Light leaving that galaxy tonight isn't slowed down or lost. It's simply chasing a finish line that is now, permanently, pulling away faster than the light itself can travel. Here's the detail that makes this worse than a fixed wall. That boundary is shrinking, relative to how much of the universe remains reachable, a little more every single year. Galaxies currently visible, currently within reach in principle, are one by one crossing outside it as the acceleration continues, their light growing fainter and more red-shifted for billions of years before finally fading past detection for good. A civilization observing the sky far enough in the future would see a much emptier universe than the one visible tonight. Not because anything was destroyed, but because almost everything else will have slipped silently past a horizon that never announces when something crosses it. Run the clock forward far enough, and the implications get legitimately uncomfortable for anyone who enjoys the night sky. Trillions of years from now, an observer on a surviving planet somewhere would look up and see essentially nothing beyond their own galaxy and its closest neighbors. Every other galaxy either merged into view or permanently redshifted past detection. Its light stretched so far, it carries no usable information left to measure. A future astronomer in that era, working entirely from what's visible, could reasonably conclude their own galaxy was the whole universe. The same mistaken, small-scale picture disproven repeatedly tonight, except this time, nobody would be around who remembered it was ever any different. Nothing about the universe ending is required for that loneliness to arrive. Only more time and the same acceleration already measured, already running, already carrying galaxies past a boundary that gives no warning and issues no final signal on the way out. You happen to be alive during what cosmologists increasingly consider an unusually good window for noticing any of this in the first place. Early enough that the sky still holds a rich, dense field of visible galaxies. Late enough that instruments finally exist, sensitive enough to measure the acceleration doing the erasing. A civilization arriving a few 100 billion years later would have no supernovae like the ones from 1998 left to observe. No expanding field of galaxies to track, no direct evidence at all that a Big Bang had ever happened. They would have to take the whole idea on faith, or invent it from scratch, working from a sky that had already gone almost completely dark and quiet around them. In the 1970s, the astronomer Vera Rubin, working with the physicist Kent Ford, pointed a spectrograph at the Andromeda galaxy. The same spiral you learned tonight is already, technically, falling toward your own, to measure something that should have been routine. How fast individual stars orbit at different distances from the galactic center. In the solar system, this measurement is easy to predict, and you already know the shape of the answer from earlier tonight, even if nobody called it out directly. Planets close to the sun move fast, planets far from the sun move slow, exactly the way Newton's equations, corrected later by Einstein's, say they absolutely must. No exceptions allowed. Rubin expected galaxies to behave the same way. Stars near the crowded center moving quickly, stars out at the sparse edges moving noticeably slower, trailing behind. The stars at the edge of Andromeda were moving just as fast as the stars near its crowded center. Not slightly faster than expected, and not close enough to blame on a small measurement error. Fast enough that, by every honest calculation of the galaxy's visible mass, those outer stars should have been flung off into open space entirely, long ago. The same way spinning too fast on a playground, merry-go-round without a firm enough grip, throws a rider clear off the edge, sent tumbling into the grass. The chart astronomers draw to describe this is called a rotation curve, and for the solar system, it looks exactly the way you'd expect. A line that climbs steeply for the innermost, fastest-moving planets, and then drops off smoothly as it reaches Neptune, out at the edge, moving at a comparative crawl. Rubin's rotation curve for Andromeda did something else entirely. It climbed, and then it simply stayed flat, mile after mile outward. Refusing to drop off the way, gravity from visible matter alone said it absolutely had to. Rubin checked the math first, assuming an error somewhere in her own instrument. Then she checked another galaxy, and another, and the result held every single time, consistently. Across every spiral galaxy, she pointed the instrument toward, decade after decade of careful, repeated measurement, the only way to explain stars orbiting that fast without being flung outward into open space was if far more mass was actually present than any telescope could ever account for by counting stars, gas, and dust. An effectively invisible halo of extra material, several times heavier than everything visible combined, wrapped around every galaxy in the sky, contributing plenty of gravity while contributing not one single photon of light for you to ever see with your own eyes. Picture that halo the way you'd picture the room you're lying in right now. If 9/10 of its actual mass were somehow invisible, the furniture, the walls, everything you can touch and see, entirely outweighed by something occupying that same space that no instrument in the room could ever register. That's the situation every visible galaxy in the universe, including your own, currently sits inside of, indefinitely. If dark matter is real, and the gravitational evidence for it is about as solid as evidence gets in astronomy, then it should be passing through everything, constantly, including the room currently holding you. Physicists have spent decades building instruments specifically to catch one of those passages directly, rather than inferring the effect secondhand through a galaxy's rotation. The experiments share a strange requirement: depth. A detector called XNONT sits inside a mountain at Italy's Gran Sasso National Laboratory, shielded by nearly a mile of solid rock. Another, Lux Zeppelin, occupies a former gold mine in South Dakota, sunk almost as deep. Both bury enormous tanks of ultra-pure liquid xenon far below the surface for the same reason. Ordinary cosmic radiation, harmless background noise raining down constantly at the surface, would completely swamp the impossibly faint signal these instruments are hunting for. Only a mile of solid stone blocks enough of that noise to have any chance of hearing something rarer underneath it. What they're listening for is a single atomic nucleus, jolted by the faintest possible nudge as a hypothetical dark matter particle passes straight through the tank and, once in an almost unimaginable while, actually collides with something solid instead of continuing straight through undisturbed. Decades of increasingly sensitive runs, each one ruling out a wider range of possibilities than the last. Not one confirmed direct detection yet. From any experiment, anywhere, despite dark matter's gravity being about as well established as anything in this episode. The gravity is undeniable. The particle causing it has never once introduced itself. Some physicists have started asking a harder question underneath the search. What if there is no particle to find at all, and gravity itself behaves slightly differently at galactic scales than Newton or Einstein ever accounted for? That alternative, usually grouped under the name modified gravity, has never managed to explain the full range of evidence as cleanly as invisible mass does. It struggles badly, for instance, with clusters of colliding galaxies where the gravity and the visible matter have been measured sitting in two different places entirely, exactly what you'd expect from an invisible substance that passed through the collision while the visible gas collided and slowed down. Most of the field still bets on the particle. Nobody has been allowed to stop asking the question, because after 50 years of silence from every buried detector, betting on an unconfirmed particle is itself an act of faith in the data, not a proven fact. Either possible answer, the particle, or modified gravity would rewrite a real, substantial chunk of modern physics the moment it was finally confirmed by anyone. That's the part worth sitting with before moving on. An entire branch of science has built enormous, mile-deep instruments, trained careers, and organized decades of research around a substance nobody has ever directly touched, purely because the gravitational evidence for it refuses to go away no matter how many times skeptics have tried to explain it another way. Physicists eventually settled on calling that invisible material dark matter, and the name is really just an honest, plainly stated label for ignorance, chosen carefully to describe the one single thing known for certain about it. It doesn't interact with light in any way at all, neither absorbing it nor reflecting it, nor emitting any of its own, which is the only reason it took until the 1970s for anyone to seriously notice something that outweighs every visible star in the universe put together. The Swiss astronomer Fritz Zwicky had actually spotted hints of it decades earlier, in 1933, studying how galaxies moved inside a distant, densely packed cluster and finding far too much gravity holding the whole thing together for the visible mass to honestly explain. But his results were mostly dismissed for nearly 40 years. It took Rubin's precise, repeatable measurements, galaxy after galaxy, to finally convince most of the field that the missing mass was real and not a measurement error waiting to be corrected away. Now bring back the other invisible number from earlier tonight, the one about vacuum energy that promised to return wearing a different name. Add dark matter's share of the universe to dark energy's share, the mysterious pressure pushing space apart, discovered through those 1998 supernova observations. And the two invisible, unexplained ingredients together account for roughly 95% of everything that exists. Ordinary matter, every star, every planet, every comet, every single atom currently making up your own body, and everything else you have ever personally touched or seen makes up only the remaining 5%. You heard that exact number in the first 30 seconds of tonight, stated as a bare, unexplained fact with nothing attached to it yet. Here is the explanation. And it isn't really an explanation at all. Dark matter has never once been directly detected by any experiment ever built specifically to catch it, despite sensitive detectors buried deep underground specifically to shield them from every form of interference physicists could think of. Dark energy is, at best, a placeholder name for the exact same mismatched vacuum energy number from earlier, off by that impossible margin of decimal places, dressed up as a measurement instead of a mystery. Two invisible things, discovered indirectly through their effects on everything visible, making up 19 times more of the universe than everything you could ever hope to see, photograph, or touch with your own two hands. Sit with the actual shape of that admission for a moment, because it's larger than any single fact tonight has asked you to hold. Every telescope ever built, every observatory, every mission launched specifically to look outward, has spent its entire existence studying a 5% slice of what's actually out there and calling that slice the universe without bothering to mention the footnote. Not because scientists were careless, or because the missing 95% was hiding especially well, because every single tool ever built to detect light can only ever detect the small fraction of existence that happens to interact with light in the first place, by definition. 12 corrections across a single night, and it's worth finally saying as one sentence what took 12 to actually earn. You were never taught that gravity bends space instead of pulling it, or that a comet's tail leads the way instead of trailing behind it. Your own yearly orbit, you assumed, closed into a neat circle. A clock on a shelf seemed to keep the same time as one on the floor, and an orbiting station looked simply parked in place, needing nothing to stay there. The scattered rock of the asteroid belt read like the wreckage of a planet that never was. A vacuum passed for genuine nothing. A black hole seemed to reach out farther than an ordinary star of equal mass ever could. Your own galaxy looked like a finished shape, not a meal still being eaten. Somewhere out in the dark, an explosion supposedly happened. Once, in one place. The visible edge of the sky stood in for the actual edge of everything. And what your own eyes could see became, without anyone deciding it on purpose, most of what you assumed existed. You were taught a smaller, sturdier version of each of those 12 facts, sized to fit inside a classroom, a childhood, a single human lifespan too short to watch a comet complete even one full orbit. A few of tonight's corrections went deeper than that headline 12. Mercury's stubborn orbit, a wind first noticed in a comet's crooked tail, a belt with lanes carved out of it, a second galaxy already closing in, a glow that only makes sense with an extra chapter attached. a horizon steadily erasing tomorrow's view. Every one of them, small detour or main event, traced back to the same underlying mistake. Early tonight, this episode promised not to resolve something. Why finding out you were wrong about your own universe felt less like losing something and more like being let into a bigger room. Here, finally, is as close to an answer as tonight has to offer. Losing a fact costs you something you already had. Losing a simplification only costs you the wall that was standing between you and a room that was there all along, lit the entire time, waiting for the wall to come down. Let that arrive slowly, because it changes what the word wrong in tonight's title actually meant. What you were taught was never a lie. It was a simplification the universe itself has spent the last century steadily outgrowing, one measurement at a time, a black hole photographed, a satellite's clock corrected, a star's light bent around an eclipse, a rotation curve that refused to slow down. And tonight, in the space of a couple of hours, so did you. A universe, it turns out, is not a fixed backdrop that objects move through while some observer watches safely from outside it. It is the thing doing the moving, the bending, the falling, the stretching, the forgetting to stay empty, and nobody gets to stand at the edge of it holding a telescope, purely as a visitor. Every one of the 12 corrections walked through tonight, from the very first to the very last, described something actively happening to matter, to light, to distance, or to time itself. All 4 of those things are, right now, still happening, inside the same 5% of ordinary matter currently arranged into a body listening to this sentence, on a planet currently falling around a star, inside a galaxy currently eating its neighbor, inside an expansion that began everywhere at once, including precisely the patch of it currently being occupied. That's the actual answer to the question this whole night was built around. Underneath the 12 smaller ones, not how much of what you knew was true, but where the line between watching the universe and being part of it was ever supposed to sit. Tonight's answer is that the line never existed in the first place. It only ever looked that way from a simplified enough distance. What you were taught was never a lie. It was a simplification the universe finally outgrew, and somewhere across the last couple of hours, so did you. We've drifted tonight from the weight pressing you into whatever is holding you up, through a moon that never stops falling, past a comet towing 2 tails toward nothing it's actually chasing, out along a spiral no diagram ever drew correctly, into a vacuum too crowded to call empty, across an event horizon that isn't a wall, through a galaxy still finishing a meal it started billions of years ago, back to a beginning with no address, and finally out to the edge of everything anyone will ever get to see, only to find that edge isn't an edge at all, just the current limit of how far the story has traveled to reach you. None of it happened somewhere else, to something else, while you watched from a safe distance. It happened, and is still happening, to the only universe there has ever been, the one holding you right now, exactly as much a part of tonight's 12 corrections as any comet, any galaxy, any collapsing star. Somewhere behind you tonight, a satellite is still falling in slow motion. Somewhere ahead, a smaller galaxy is still losing stars it will never get back. Somewhere in the room around you, empty space is still pushing back against itself, exactly as hard as it always has, whether anyone is awake to notice or not. None of it needs an audience to keep happening. It simply keeps happening, patiently, the way it always has, long before tonight and long after. If your eyes feel heavy, let them close. The rest of what's out there will keep existing whether anyone tonight is awake to watch it or not, the same way it always has. If this felt like home, leave a comment when you wake up. The universe will still be here when you wake up. So will we. Good night.